Exercise 38, question number 5. This equation that you have here that we're going to investigate highlights a situation in engineering where we might well use this situation to come up with a graph to plot resistance against temperature for a particular material. We look at the formula that we have at the top here. The resistance of some metal or some component equals R0, the initial resistance, i.e. temperature 0, times 1 plus alpha, which is the coefficient of resistance or resistivity for the material, times T, the temperature. 4 unknowns, but if we're given 2 of them, which we are, we're given 2 situations. What's the resistance of this particular component at 30 degrees? What's the resistance at 100 degrees? We can form 2 simultaneous equations and find alpha and R0. Once we've got those, then as you'll see, I'll go and show how this works. You can plot a graph of resistance against temperature, and then we can use that graph to find values, which is a sort of thing that goes on in the advanced maths on the BTEC course, or certainly on other engineering maths courses. So let's try solving these simultaneous equations. Let's form the 2 equations first. So given this first situation, we've got that 25.44 equals R0, 1 plus alpha and T. T is 30, so let's put the 30 first and then T for temperature. So that's equation number 1. And then the second equation from the second scenario, 32.17 equals R0 into 1 plus 100T. So that's equation number 1 and equation number 2. Now, the easiest way to solve this, if you look at equation 1 and equation 2, if I were to divide one equation by the other, then I would get a situation where R0 has disappeared, and then I could find T. So let's try that. If I divide equation 1 by equation 2, to make sure I try and keep whole figures, I'm going to put equation 2 divided by equation 1. You'll find when you do that that R0 cancels, and then we can multiply to get rid of the denominator, or the figure underneath in the term. See if you can carry on from there and work it through. I'll carry on. So we've got 32.17 divided by 25.44 equals R0, 1 plus 100T, over R0, 1 plus 30T. Now if you look at the right hand side, we've got a factor of R0 top and bottom, so I can divide top and bottom by R0, which effectively cancels out the R0s. So now I've only got one unknown. I've got that 32.17 over 25.44, which I can work out, equals 1 plus 100T over 1 plus 30T. Multiply both sides by 1 plus 30T to get rid of that at the bottom, and then carry on. See if you can go from there. I'll pause. So 1.265, holding the same number of significant figures, equals 1 plus 100T over 1 plus 30T. Multiply both sides by 1 plus 30T. We get 1.265 times 1 plus 30T equals 1 plus 100T. Now multiply out the bracket on the left hand side and then collect together like terms, get the t's together on one side and numbers on the other, and you can find a value for t. See if you can finish it from there. I'll carry on with the solution below. So multiplying out the brackets, I get 1.265 plus 30 times 1.265, pause, 37.95 T equals 1 plus 100 T. And now subtract 37.95 T from both sides, subtract 1 from both sides, and we get 0.265 equals 100 minus 37.95, what's that? 68.05, is it? For Tiltech, it's 62.05. So now what's T? Divide both sides by 62.05 and I get T equals 0.265 divided by 62.05, which equals 0.00427. So 3 significant figures, which is pretty well the solution in the textbook, just a rounding issue. So that will be degrees centigrade. That's the temperature. Now we can plug that back in, the value for temperature in one of the original formulae, 1 or 2, to find out the value for R0. I'm sure you can carry on and finish that from there. So now let's move on and have a look at what happens when we plot these values out. So we go to autograph. So if we fire up autograph, what I can do now is put in this equation. So the equation I'm after is R equals R naught 1 plus alpha T, but now we know what alpha and R0 are, so we can write that R equals R0, which when you calculate it turns out to be 22.56 using the values in the textbook. 1 plus alpha, which was 0.00426 using their value, puts at T. So that's the equation we're going to put into autograph. We want to find out how the resistance varies with the temperature. So temperature, we're going to let that be the independent variable, so that's going to go on the x-axis, and we're going to see what the resistance is as the temperature changes, so that's going to go on the y-axis. So autograph only recognizes y and x in variables, so what we're going to type into autograph is y equals 22.56 1 plus 0.00426x. So let's type that into autograph. So to do that, we enter equation, which is this button here, and then we type in y equals R0, which was 22.56, so 22.56, open brackets 1, plus 0.00426x, close bracket. And then we'll hopefully get a straight line. So if I key it in, at the moment we're getting nothing at all, so let's zoom out and see what happens. There's the line. So if you can't see the line, you use this zoom out button here to zoom out and see the graph. I can shift it around using this hand here, and so now we've got temperature along the x-axis and resistance along the y-axis here. All the resistance seem to be in quite a small area here, a small area of resistance. So at 0, what's R0? That's the point at which it cuts the y-axis, so that should agree with our R0, 22.56 cuts there. But then the resistance is only going up to just over 30 ohms in this quite a big temperature band. So we could do with zooming in on this y-axis. So that's this button here, zoom in on the Y button. So if we do that, we'll see that the graph opens out. And so we're really only interested in what happens from 22.56 onwards. You can look at the bottom, we can see the temperature now. So now it's giving us more accurate values for the resistances at certain temperatures. So I've got a graph now that I can use. What is the resistance at 50 degrees centigrade? About 27.5 ohms. What's the temperature? When the resistance is 33 ohms, I can look across from 33 ohms and down, and I see that I'm just over 100 degrees, about 108 degrees, something like that. So there's real value in using simultaneous equations in a question like this to end up with a function that describes the resistance and temperature of a material. So I'll put this into my document. So if I wanted to do this into a Word document, oh no, probably the easiest way to do it actually, well for me, is to put this in and paste it in. But if you want to do it into a Word document, you would go to Page, Copy Page as a bitmap, and then you can put it into Word and cut and paste as usual. So there's the function, where those lines came from, but that's what you're looking for. So you can now use that function graph to find out values of resistance and temperature. I'll pause here and tidy that up. Okay, so there's the function. There's the function. Okay, so here we have resistance we're plotting in here, again in degrees, in ohms rather, same, in ohms. Against temperature in degrees centigrade. And so we can use the graph to find out, say, what is the temperature when the resistance is 30 ohms there. What is the resistance when the temperature is 50 ohms there. So I can use the graph to find values.